All right, guys, so last time we didn't quite finish 6-3. Do you guys remember what's happening on Tuesday? Quiz, good. All right. It's going to be on 5-2-6-1-6-2. What's happening a week from that Tuesday? No. A holiday. Yeah. So here's the weirdness. We're going to have next Tuesday, Thursday, and then next Tuesday's a holiday. That's the 11th. And then that Thursday is our test. Yay! So obviously, next Tuesday is the last day for new stuff before the test. I'll have the practice test. Next Thursday is going to be the review day for the test. You with me? And then, of course, since Tuesday's a holiday, the test will be Thursday. Sorry, I might have just said next. You know that Tuesday's a holiday. So we're doing. No surprises there. It's been on your homework sheet for a while. Okay. So no other questions from homework? I'm taking it. Has anyone recently gone to the Math Science Center for the first time to get some help? We don't trust those people, Jeff. All right. Okay, so we're right in the. Today is going to be an interesting transition day because today we're going to finish talking about fractions for the moment. We're going to get into decimals. So we're going to make that transition today. We're going to revisit some old friends we met along the way.
Yeah, Jeff.
I think the last thing I talked about, let me see if I can overlap with past me. By the way, let's do this real quick. Oh shit, I should probably do this. Oh boy. Oh yeah. There we go. Okay. So I haven't talked directly about properties of fractions. Do you guys remember what this property was all about? This has come up a few times. In the room. Where? You have to go outside to do what? So in this case, what do you think's in our room? Fractions. Yes? When I add or subtract two fractions, will the answer, so let's just talk about addition. If I add two fractions, is the answer a fraction? And this is where you gotta remember. So for example, 1/2 plus 2/3 is gonna be a fraction. What do you do? What's 1/2 plus 1/2? Is that a fraction? Yes, it's 1/1. We just don't write the over 1. You with me? So you just gotta remember that. So closure's all about, if you operate on two elements, is your answer still that kind of element? Fractions are closed under addition because even if they add to be whole numbers are just special fractions where the bottom's 1. You guys with me? The only way this could be broken is if I did 1/2 plus 2/3 and my answer was pi. Because pi is not a fraction. You with me? Because pi is not a whole number. You guys all with me? So I'd have to add 2 and they would come out to be something that's not a fraction. Okay, but every fraction, when I add two fractions together, I get a fraction. Okay, and then if I multiply two fractions, do I get a fraction answer? If I multiply two fractions, do I get a fraction answer? Yes, so it's closed under multiplication, so it's closed under addition, multiplication. When I divide two fractions, I get a fraction answer. This book is still a little weird about negatives existing. They're kind of assuming we don't know yet that negatives exist. So technically, when you subtract two fractions, you could get a negative fraction, but we know there's a freaking fraction. So it's still closed under subtraction also. Okay. The only issue you might have with division, what's the only thing that you might have an issue with division? Same old thing that you have an issue with division all the time. What's the one number that screws the division up? 0. But is 0 a fraction? Of course it is. 0 over, no. Yeah. Quick. Is everybody still with me? I could put any whole number in a 0 whole number. Yes, it's the name of the whole number comes from the fact we added 0. So 0 is a fraction. But what do I get when I try to divide by it? Undefined, right? Okay. So division is technically not closed because if I take a over b divided by 0 over 1, I get undefined. Okay. So closure still means the same thing it always did. Closure doesn't give a shit what we're working with, in this case fractions, and what we're doing with them. Fractions are closed under addition, fractions are closed under multiplication. Now we know fractions are closed under subtraction, that's fine. But fractions are technically not closed under division because there is a fraction if I divide by it, things go to shit. You guys okay? This says, UND, undefined. Yeah. Okay. And then very quickly, all the other stuff. I'm gonna have a bunch of them right here. So, commutative, associative, distributive. What about the identities? What's the additive identity? It's still, what is it still? What do I add to maintain something's identity? It's 0. What's the multiplicative identity? It's still 1, yes. So we just added new elements to the bunch of numbers we're playing with. We were playing with 1, 2, 3, 4, and then we added 0, and now we're adding fractions. But they still operate with, if I multiply a fraction by 1, it's still the same fraction. Blah, 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 blah. Here's the one new thing. So this is still 1. This is still 0. What about the multiplicative inverse? So just to remind you guys, if I establish an identity with an operation, the inverse for that operation is the thing that brings you to the identity. What the shit? So, for example, the additive identity is 0. So what's the additive inverse? Let me start there. What's the additive inverse? For, let me see, for, let's do an example, a nice concrete example. What's the additive inverse for 2/3? What do I add to 2/3 to make it become 0? Negative 2/3, good. So this is a little bit early because the book still doesn't let us know that negatives exist. But let me just start there because that one's easier. Multiplicative inverse would be the number that I multiply to get me back to the multiplicative identity. So inverse should tell you we're undoing something, right? When you hear the word inverse, that should mean opposite somehow. There's two ways to be opposite. I could either have the opposite sign, or what's the other one? You guys know, what do I multiply 2/3 by to make it become 1? 2/3 becomes 1. Yeah, 3/2, the reciprocal, yes? So the other name for multiplicative inverse of a fraction is reciprocal.
So what's the multiplicative inverse of AB? A over B? That's insane. Okay. Got it. So when you're in my class, how do you know you're right? If I call you insane, you are correct. Okay, so no big surprises here. Multiplicative inverse is the technical correct name for reciprocal. We just say freaking reciprocal to just talk every day. Or you can even just say flip. That's cool. Okay. All right. So I think one of the last things I talked with you last time was I all of a sudden asked you if I had 8 chairs divided by 4 chairs, that would be 2, right? If I put 8 chairs into groups of 4, I can make 2 groups, right? So 8 anythings divided by 4 same things. 8 people divided by 4 people is 2. That's crazy. So what is 8 thirteenths divided by 4 thirteenths? Whatever you're thinking, right? Nope. 8 people divided by 4 people is 2. 8 chairs divided by 4 chairs is 2. 8 thirteenths divided by 4 thirteenths is 2. Think about this. If you put 8 thirteenths into groups of 4 thirteenths, how many groups could you make? 2. Remember division, this is measurement division? Yes? Okay. Boom. I'm going to be overlapping a bit too much. I think I am overlapping a bit too much. We'll get there. Yeah, I think we did. Okay. This is fine. So then A over B divided by C over D is A over C. Okay. Pretty sure we talked about that last time. Trying to feel out where I left off. Yeah, that's right. We did that. Okay, good. So if I want to do, for example, 24 35ths divided by 8 sevenths. Why can't I use that rule we just talked about? Damn it, Jeff. There should be a B, guys. I got so stuck in my own alphabet. If the bottoms are the same, the answer is just the ratio of the tops. Yes? We actually know why that is. We know how to divide fractions. This is not a surprise. The B's would cancel. Yes, yes. But you can see how that just makes physical sense. Before you tell a student about multiply by the reciprocal, you could just start with something physical. 8 chairs divided by 4 chairs. I mean, that's 2 groups of them. So what can I do here to be able to use this? What could I do to this so I could use this idea? Common denominator. And what does this need to become a common denominator? 5. So then what would you get? If you apply the rule, what would you get? Are the bottoms the same? Yes. So what's A over B divided by C over B is A divided by C. Do it again. No. Don't go there. Don't plug it in your calculator. What did you plug into your calculator? Yes. Cool. That's the answer. And then what do you do with that? You don't make it into a decimal. Simplify it. What goes in a boat? Real quick. How far apart are 24 and 40? What's 40 minus 24? 16.
So either 16 goes into both. Can you very quickly see 16 does not? Okay, 8. So this is a cool trick. I keep bringing it up. You don't have to ever apply it in your entire life. But if you try to reduce a fraction, if you take the difference between the top and the bottom, the thing it can be reduced by has to be a factor of what you get. So if this is reducible, it is reducible by a factor of 16. It's not 16, the next number down that's a factor of 16 is 8. And sure enough, 8 goes into both, yes? You guys see that? And again, that's a thing you never have to use. If you don't want to, you don't have to. Don't use it, I don't care. I want you to know it exists. And then you can go, I don't like that, I'm gonna forget about that. Screw you, Jeff. That's beautiful. Tears. You make your own choice. And you're all like, he seems to like when I say Scrooge. No, that's not the point. I want you to be aware something exists and consciously make the decision to use it or not. So I can divide by 8, and I get 3 bits. Okay. Now, in this process, we of course get to the point where we do better. And this is what I think I talked about last time. I've proven this a few different ways. So I think I've caught up to myself now. What is the kind of correct way to do this? How do I divide fractions? What's that? Not eat, pray, love. It's keep, change, flip, yes? A little more boring, but oh well. So if I keep, change the operation, flip the fraction, what could I do now? Do I just want to multiply across and get these big ass numbers? Hell no, I'd much rather cancel first. So if it's on the bottom, it's dividing. If it's on the top, it's multiplying. Division and multiplication, opposite operations. That's why I can cancel any common factors between the top and the bottom. So what about 8 and 24? 8 goes into 24. Sweet, 7 goes into 35. And then you get 3 times 1 is 3, 5 times 1 is 5. We get 3/5 again. Yay. Okay. That's the ultimate end place you get to. This is another example of before you are there with your students, a parent might look at what you're doing with them and say, why the shit don't you just tell them to multiply by the reciprocal? And you're like, slow your roll. I'm glad you're not a teacher. You gotta get them there. Right? Much more valuable a student understands why something works, not just knows what to do. The more you agree with what I just said, now that makes it sound like I'm the arbiter. It's just a good thing, kids. Okay. I think. Sorry, did I take that one too quickly? You guys good? Okay. Did I do this yet? Yeah, I don't think so. What if I try to do this? 4 divided by 1/3. What if I try to represent this visually? 4 divided by 1/3. Before a student knows what we just talked about, right? How do I represent this? Well, real quick, how do you represent 4 visually? Guys, how do you represent 4? 4 squares. Yeah? Don't make me draw too much 3D. Alright, so 4 squares. 1, 2, 3, 4. So real quick, what is 6 divided by 2? 3, because 3 2s make 6. 6 has 3 groups of 2 in it. So if I'm doing 4 divided by 1/3, I'm curious, how many groups of 1/3 does 4 have in it? Let me say this again. 6 divided by 2 is 3, because 6 has 3 groups of 2 in it. Is that cool? And let me give you a visual on that before we do this. So 6 divided by 2. 1, 2, 3, 4, 5, 6.
It has 1, 2, 3 groups of 2. Yes? Okay, and we talked about that before, how to divide visually, set method, blah, 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 blah. But now, do I see any thirds yet? I have to do something for myself so I can see some thirds. Yes? What do I do? Yeah! I want to go this way for some reason. I will calm down eventually. Now I can count some thirds, right? You guys with me? So, okay, this is the key with teaching this for understanding instead of just memorizing and doing. Memorize and do is nowhere near as good as understanding. 6 divided by 2, they're going to go into this shit knowing you're going to have done all the sharing and the measurement division with them, right? You're going to give them Oreos and say there's 5 of you. You want to be fair, and then you're going to get the kid trying to eat them. Stop. You're going to have them divide stuff physically. Yes? They're going to come into this totally getting that. 4 divided by third, well, 6 divided by 2 is easy. I can see groups of 2. 4 divided by third, I can't see any thirds. Let me break them up. Now just count. How many thirds are there? How many thirds are there? Well, 12. Yes? Now, of course, we all knew the answer is going to be 12. But you see, it's really nice to see you can get it visually. You can get it physically. Yes? So sure enough, there are 12 1/3 and 4. Therefore, 4 divided by third must be 12. That lines up with what? 4 divided by third is 4 times 3. And that's a physical representation of why it makes sense to flip. Each one of the 4, I actually made it worth 3 times as much. Do you see that? I'm talking about thirds. They're each worth 3 thirds. So 3 times 4 is me going, oh yeah, I cut each one into 3 parts. So of course there's 12. Okay, maybe we stop. This is what people don't understand about, like 4 divided by 1/3 is easy. Now. But we're talking about people that have just barely started talking about fractions themselves. Yes? Okay. All right. So what about this? Let's take it one step up. This is where I don't think we've talked about it yet. Look at this one. 4 divided by 3/5. Go ahead and draw that out. What are you first going to draw? 4 squares, yeah. Megan's like, come on, Jeff, let's go 3D, man. Or you don't have to draw it, I guess. So draw the 4 squares, and what do you think you have to break them up into? Don't overthink it. I first start breaking up into 5ths, yes? Okay. Do you see how this is a harder problem, though? Okay. Let's see if you guys agree this is going to be nifty. Since I got to break them up, I'm going to give myself rectangles, yes? So I can kind of work with them a little easier and give myself no room, too. Why not, Jeff? There. 4. And I'm going to break them up 1, 2, 3, 4. 1, 2, 3. That's so helpful, Jeff. Keep saying it out loud. I'm sorry. Okay. So I cut all my parts into 5 pieces. What do you think you do now? What am I looking for groups of? Oh, yes. Do it again, sorry. Oh, you could, but there's a slightly, I would just end up with all of them shaded, almost. And then it wouldn't really help me keep track. What am I looking for exactly? How many groups of 3/5 are there? So I want to keep track of how many 3/5 I can find. Yes? So one way to do that is 1, 2, 3. There's one group of 3/5 right there, yes? Now do you see what I have to do? Where's the next group of 3/5? 1, 2, 3. There. Yes? Isn't that 3/5? It's okay if I have to go to the next thing. I'm just looking for 4. The totality of 4.
how many groups of 3/5 does it have in it? I should have asked you guys, first thing today, I should have said, do you think we could do 4 divided by 3/5 visually? No, you guys know we could, because we've done some weird shit. Keep going, oh wait. You get to an issue. Have you guys gotten to an issue yet? There's going to be an issue at the end. What's the issue at the end? Yeah, you said it perfectly. So how many groups of 3/5, whole groups of 3/5 do we have? Yeah, 1, 2, 3, 4, 5, 6. Now here's the trick. Let me see if you guys are with me on this. To make a full group, alright, this is the weird part about this visual. How many slices to make a full group of 3/5? How many, so I sliced each of these, yes? Slice it. How many slices to make a full group of 3/5? 3. Is there any way? Out of 3 that I need, how many do I have at the end? 2 out of 3 that I need. Oh, some of you guys going. And over here I got the, oh, no, wait a minute. Keep going. This is the trippy part. We see the 3/5. How do I interpret the leftover them, right? It takes 3 slices to make a full group I'm looking for, correct? I'm looking for groups of 3/5. So when you're at the end, you're like, how close was I, or how far off was I from having a full group if I have some left over? I'm 1/3 away from having a full group, yes? So I'm this is 2/3. So it's 6 and 2/3. All right, can you check that for me? Can you actually do 4 divided by 3/5? Can you do it? Keep, change, flip. Eat, pray, love. Stop, drop, and roll. Whatever they call. Apply the one that's correct in the situation. Does everybody understand what I want you to do? Mathematically do 4 divided by 3/5. Just do it directly. Do it directly. So 4 divided by 3/5 is 4 times 5/3, which is 20 over 3, which is a mixed number. 3 goes into 20 6 times with 2 left over 3. Thank you. That is kind of cool. I know I'm a math guy. I'm gonna find all kinds of weird ass shit cool. But it's really neat. There's no way in hell that most people walking the street even remember how to do 4 divided by 3/5, let alone can imagine there's a visual way to do it, yeah? Okay, maybe. So real quick, what could you sit down, what could you put in front of a student, manipulative-wise, that would lead them to be able to do this? There's a really, really good option. All the manipulatives we've seen, even stuff we've seen and not been able to play with too much, I'll tell you, it's not the fraction manipulatives, right? Do you remember a while back we were watching and there was a whole block of time where I think it was the little girl that was clicking these things together? Do you see how those would be perfect for this? Because if you click
and make four groups of 5. That's essentially the same as being able to chop into the fists, correct? And then she could, I'm gonna put her in my head, she could tear them apart in little groups of 3, yes? And then she'll go, up, 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 and I got 2 left over. You guys kind of follow what I'm saying? So I mean, you could do 4 divided by 3 fists completely physically. And that is cool, so I appreciate it. Even if you just said it because you saw I wanted you to, it's okay. All right, that's really neat. Okay. Maybe. Blah, 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 Jeff. Let's see. Blah, blah. There we go. Okay. So this is obviously a really good candidate for a problem for you to do in something. Test or a quiz or something. Okay. Let's see how much I want to say. Oh, let me see what you guys think about this. Same old strategies coming back. By the way, today's going to be a lot of me talking, so just get used to it. I'm sorry. The deep sigh that happens after that. So if I had, for example, well, let's do it like this. Uh-oh. You can do it. Come on. You gotta really mean it. You're okay. So I mean, what idea is happening here? I would tell you to do this without a calculator. Yes. What would you do? Yeah. So this is another one of those. So now, I can't remember if I did a lot of these with fractions, but this is just more of those thinking strategies about commutativity, associativity. What are my compatible numbers here? Oh, okay. There's actually 2 ways to do it the way that I set this up. 25 and 28 are sort of compatible. You can use compensation between the 2, but I kind of want to get that 1/7 dealt with. So I'm going to focus on what's compatible with 1/7? 28, because 20 is divisible by 7. So if I use commutativity and associativity to get this sucker to look like this, what's 1/7 times 28? 4. 4 times 25? 100. I'm not sure why the 100's mad. 100's angry about something. What do you guys think about, let me just throw this at you, why not? If you had to do this by hand. Instead of starting with, oh shit, improper, and then I gotta do reciprocal. No. You only do that if you can't do what you can do here. I'm divided by 4. You see numbers that are divisible by 4? What does 32 and 8/9 mean? 32, what operation? 8/9. Huh? Addition. 32 plus 8/9. Do you guys remember that I can do right distributivity of division? Remember that? So I can do 32 divided, what's 32 divided by 4? So 32 divided by 4 is 8. And what's 8/9 divided by 4? 8 things divided by 4 is how many things? 2 things. So our standard way of doing things very often is the way we do things when we can't do them the easy way. Yes? So don't just always default to, okay, improper fraction, reciprocate, blah, blah. No, say, wait, everything's divisible by 4, let me just do that. Okay, I got 2 thumbs up from Grace so far. What about, oh, that's kind of stupid. I'm not gonna do that one. I just had another one that's sort of like this. Okay, nothing too crazy there. Alright, so now let's get into chapter 7. Chapter 7 is decimals. I think I already told you guys that the next test is not going to go all the way through 7-4. There's no way in hell we're going to make it there. I'm not certain right now as I stand here how far we're going to make it, but we're not going to make it to 7-4. Either 7-2 or 7-3, we'll see. Can you guys just help me? Just help me, dear God. How do I tell what places these are in? What place is this? Tens. What place is this? Ones. Tenths. Good. Yeah. Right? We develop the lisp when you get back here. Thousandth. Hundredth. Okay. And of course, that's because if it's going to fit in our base 10 number system, if I have more places, I keep dividing as I go left. We divide by 10 as I go left, Jeff. Good. As I go right. Yes. So here's the thing to realize. Decimals are fractions that fit into our base 10 number system. Obviously, if it has a 10, 100,000, 1 followed by zeros, it's automatically, on the bottom, as a fraction, it's automatically a decimal. Yes? Can you guys write 7 10,000ths as a decimal? Does anyone know the shortcut to do that? What you got?
Actually, it might not be a shortcut. I just put a 7 in the 10,000 place and just put zeros.
Oh yeah, but that means you got to find the 10,000 place first, which is a little trippy. But it's not that bad. You go tens, hundreds. How many zeros are down there? That's how many times I move the decimal place. So like, if I put my 0 point, the 7 will be in the 4th place over, because there's 4 zeros. Or like you said, you count it out, tenths, hundredths, thousandths, 10,000s, but that's 1, 2, 3, 4, right? So the number of zeros, that's a beautiful way to kind of like quickly figure out where things are supposed to go. Now, the reason you have to be careful with that though is, how would I do 257,000? How would I do 257,000? Yeah. The last digit has to go into that spot. So there's 3 zeros. The last digit must go 3 places in. So the 7 has to be in the 3rd place, so 257. Right. And real quick, why the shit is that? Why? Do you see how a student, you got to start thinking about like, as a person seeing this for the first time, or maybe some of you guys are like, yeah, why? Why is it dependent on the last digit? Well, real quick, 0.257. Which way do I want to go with this? I'll go the other way. 257 over 1,000. I'm going to go on a limb and say you all would agree with me that this is 200 plus 50 plus 7 over 1,000. Is that acceptable? Okay. Is everybody with me? And I don't know how you think when I go on these little side notes, but this is huge. This is kind of big because you have to be ready for the weirdest questions from your students. Does everybody agree that each of these 3 is being divided by 1,000? Isn't that what that says? So I have 200 divided by 1,000. I have 50 divided by 1,000. Jeff. Yes, and I have 7. What, Jeff? You're fine. And what principle does this way of looking at that number, the 0.257, what principle does it relate back to that I keep talking about? Bring it back to what they feel comfortable with. Right before decimals, they will have studied the hell out of fractions.
They feel comfortable with that fact. They all have the same LCD, you put them together, that's how you get 257, I'm cool with that, right? Can you reduce those fractions? How does this reduce? How many zeros die? How many zeros die?
It's 1/5.
2 zeros die. Don't go too far. That's 2/10, yes? What is that as a decimal? 2/10. 0.2, yes, 2/10. You with me? If you reduce 50 thousandths, what is that? 500ths, is that cool? I'm not reducing because then it wouldn't fit into a decimal, it wouldn't fit into our base 10. I'm not going to reduce. What is 500ths as a decimal? Yeah, 0.5. It's the second place in, right? Do you see now I'm dealing with one digit at a time? Which students don't, I don't know if you guys are understand. This was really easy. This would be really easy for most people once you tell them, oh yeah, 7's got to be in the 10,000s place, tenths, hundreds, thousands, 10,000s, okay? A single digit, very easy to see. I have personally had students, especially when I used to be able to teach math 88, when that used to exist here, which is like pre-algebra, that didn't understand, okay, this is 3 digits. Why is it not 00257? Do you see what I mean? Do you see how somebody might think that? So if you can rewrite it as fractions, which they're more comfortable with, reduce them, and then show them, look, 2/10 is 0.2. 500ths is 0.05, it's in the second place. And then of course 7 thousandths, that does go into the thousandths place. Thousandths. I don't know, are you guys kind of with me? You guys kind of with me? Maybe, okay. This is the kind of logic misapplication you're going to have to be ready for. To explain, if a student put 0.00257, because they're thinking, oh, the 2's got to go in the thousandths place, yes? No. This is what it's built off of. It's the last digit that has to go into that place. Okay, maybe. So, real quick, before I do, maybe I'll do this first. Let me start with a weird question. Okay, here's our little friend. The unit, yes? The little absolute unit, the little blue dude. By himself, that doesn't mean anything decimal at all, right? It means 1. When I do look at him in relation to one of these, why can I suddenly say this might be a decimal? If these are my 2 pieces I'm considering exist in my universe, if I consider this to be 1, what's that? 1/10, literally, right? It's got to be, how many parts do I need to make this? 10, and out of those 10, how many does he have? 1, so he's 1/10, poor little dude. You guys kind of with me? So this is how I can use base 10 pieces to represent decimals. If I represented everything based on this guy, what is he now? Yeah, he's 1 out of 100. He's 1 piece out of 100 that you need if you wanted to overlay this with blue. Yes? What is he now? He's 1/10 because he's 1 out of 10 pieces you need to make this. Yes? And of course, I've got to have this guy. Good Lord. And so all the same stuff applies. So what is this guy? In relation to him, this guy is now 1/10 because it takes 10 of these to make 1 of these. Yes? You guys so the way that I first introduced fractions to you guys, 1/3 is the number that it takes 3 of to make 1, for example. 5/4 is the number it takes 4 of to make 5. I mean, that's kind of like going along with what division means.
the pieces actually kind of reinforce that idea. And here, let me show you this while I'm thinking about it. There is a website called Common Core Sheets. Shit. Oh, here it is. Okay, thank God. Oh, it's over here. Watch in real time as Jeff forgets where everything is. There we go. That's base 10 pieces, right? You with me? So like, this one kind of starts in the middle of everything a bit. It doesn't really tell you what that's in relation to. But obviously, how many shaded parts are shaded? 8 out of 10. So of course that would mean 0.8, yeah. Okay, you with me? This website, I mean, when you become a teacher, and the same is true for college professors. When I teach a class I haven't taught in a while, or for example, that I've never taught before, I'll reach out to my colleagues and say, hey, does anyone have like worksheets and shit? Practice tests? Tests? You guys, you have to say anything, and then they give it. And then I modify it to be me, but I don't start from nothing. You with me? So the last thing I want any teacher to do necessarily is to just take something wholesale. You guys have to put your own stamp on it. You have to develop your own way of showing things. But dear God, when I'm about to make a worksheet, I'm like, I don't have any worksheets about this. I'll go to Google and type in, do you guys know you can do something like decimal converting to fraction, file type, star dot, doc. So it'll only give you a Word doc. Because then you can edit the damn thing. So you'll find a lot of worksheets in PDF. And I don't have the money to pay Adobe to give me the freaking ability to do that. So if you get the Word doc, you can modify it, put your own spin on it, put little pictures on there. I mean, look at this. This is so clinical. Do you agree with me? And you're like, it looks like yours. Shut up. It's actually colorful. It's yours. Be quiet. You guys aren't 7. So, you guys kind of follow what I'm saying. So you're not going to be alone. You're going to be surrounded by teachers who have a lot of worksheets they made over the years. But then you have a lot of resources like this to go to. Okay. What was the other thing? Oh yeah, this was a little bit trippy. I'll come back to this in a minute. Yeah, I'll come back to that. Okay. You guys kind of with me on how you could utilize this? So you could ask a student, if these are the 3 things we're considering, what is that? What would this be? What do one of these represent, if these are the 3 available shapes that I'm allowing? What does this represent? 1. Yes? These represent tenths. So do you see how this is the ones place, this is the tenths place, this is the hundredths place? Yes? Because isn't one of these going to be 1/100th? These are going to be 1/10th, and this is whole. He's whole. He's good for you. So what decimal is this?
1.34.
Yeah, 1.34. Kick ass. And then you can have them add decimals. Same way we did before. So you could use the same manipulatives in different ways. They don't have to represent just whole numbers. They could represent different place values. Yes? Now obviously, physically, you can't really go beyond this. So there are some physical we don't have a way to represent a 4-dimensional thing. That would be what would be required. Do you understand what I'm saying? Can't do that shit. I don't know. If you do, it might be a black hole, so don't do that. Okay. So pretty cool with that? Okay. Back to this. So here's the thing I was trying to get at earlier. Here's a really silly question. Holy shit. What number is that? 7/100ths, is that a terminating decimal? Is that a decimal that would stop? For example, real quick, do you guys know a fraction that is a decimal that does not stop? 1/3, right? Most people know 1/3 is what decimal? Point, yeah, forever, right? You put a little bar over it, meaning I don't want to write all these threes, damn it, just it goes forever. 7/100ths is obviously a decimal, that it would become a decimal that stops. If the bottom is 1 followed by any zeros, it's finite, because I can count the zeros, yes? 2 zeros means 7's in the second place in. Therefore, any denominator that has so many 10's will automatically be what we call a terminating decimal, yes? But we can go beyond that, because we know we can. What about frickin' 1/25th? Does that have a 10 on the bottom? Does that have any factors of 10 on the bottom? No. What does it have on the bottom? Factors of 5, yes? Can I make it into a multiple of 10? A factor of 10, I should say, like a power of 10. There's the right way to say it, math boy. What do I multiply by? To make it something over 100 or 1,000 or 1,000,000. What do I multiply top and bottom by to make it 4? I like it. I love you guys. You're all looking at me. I'm not sure what you're like. And it's not because you didn't know what the answer was. You're kind of like, it's freaking 4. So if I multiply by 4, what does that make sense? How many 5's are on the bottom? How many 5's? How many factors of 5? How many factors of 5? 2. 5 times 5. Yes? 2 factors of 5. What does each one need? I'm with you. Not aggregating, multiplicating. Right? So 5 times 5. There's 2 5's. Each one needs a 2 to become a 10. Yes? So of course I need to give 2 2's or 4. You guys follow? So if I had 3 5's on the bottom, I'd have to multiply by 8. I'd have to multiply by 3 2's. We'll do that next. So this one, I'll show you. I multiply by 4. That is 4/100ths, which is what is a decimal? Yes, kick ass. Kick ass. So what I was just saying was, if I had 7 125ths. I have no idea why I have such a thing for 7. I just do. What's 125? You guys remember that's the highway that's nearby, and it freaks me out because it's a perfect cube. So 125 is 5 times 5 times 5, right? So 125 has 3 5's in it. Each 5 needs a 2 to become 10. So therefore 125 needs how many 2's total? It needs 3 2's. When you multiply is? No, when you multiply 3 2's, 8. 2 times 2 times 2. So if you multiply top and bottom by 8. Let me show you a more direct way. You ready? If you rewrite this as 7 over 5 times 5 times 5, yes? And then multiply top and bottom by 2 times 2 times 2. That's 10, 10, 10, yes? 10, 10, 10. How many zeros? 10, 10, 10, yes? And what is 8 times 7? That's crazy. And then how do I write 56,000 as a decimal? 0.056. Kick ass. I need 3 places. 3 places. Give me 3 places, baby. 5 6. Okay, there we go. All right. It works the other way too, just to make sure you guys understand. What about 5 8's? What does it have on the bottom? 2 times 2 times 2, yes? What do each of those need? 5's. Because what are fractions all about on the denominators? 10's. So if I currently have 3 2's, I need to give each one of those a 5, so then it has a chance to become a decimal. You guys with me? Let that make sense? Decimals are fractions whose denominators are some power of 10. If my denominator has nothing but 2's, let me give it a bunch of 5's. Now it's got a bunch of 10's. That's a beautiful stop decimal, right? Terminating decimal. So I'm going to multiply top and bottom by 5 times 5. So the bottom again becomes 1,000. And does anyone know what 5 times 5 times 5 times 5 is? All right, everybody's like, we know you'll put it down there. And what is that as a decimal? 0.625. So, can anyone now see why this is everybody with me so far? If my denominator has 2's and 5's, I can give it however many 2's and 5's it needs, so it has nothing but 10's. And then it's a frickin' decimal. So you see that? Not just a frickin' decimal, well, one that stops. One that does not go forever, yes? So what is wrong with this poor dude? Look at this poor dude. Gaze upon this poor guy. Look at him. Look at that guy. Poor little guy. He didn't want to exist. I just wrote him down. He's like, what? What was that? Oh my God. What did I have for breakfast? So what's wrong with that from the perspective of what we're just talking about? What has he got in the bottom? 3's. Can 3 become 10 or 100? No. So what seems to be the only possible factor that I can have on the bottom for it to become a terminating decimal? 2's and 5's. The second the bottom has a factor that is not a 2 or a 5, and it doesn't reduce, it's going to be a repeating decimal. Let me say this again. The answer to that will be a repeating decimal. Yes? So every fraction in the universe is either one that becomes a terminating decimal or a repeating decimal. You guys are repeating, such as 0.3. Yes? Is everybody okay? Some of you guys look sick. I'm sorry. Alright. So what the shit is this? Well, here, let's do this. I don't think I've done this with you yet. Do you guys know what 1/9 is as, have we done this? I can't remember. 1/9 as a decimal? Oh shit, I did this backwards again. Pretend like I didn't say it. Do you guys know what 0.1 repeating is as a fraction? Yes, okay. Thank you. So, no, let's all pretend we don't. Thank you. In algebra, what do we do when something is the value? I don't know what it is. We call it x. Yes? Okay. So I'm going to say x is 0.1 repeating. Because what's the worst thing about this number is the fact that it has an infinite number of ones. You guys agree? It would be great if I could make them go away. How can I work with 0.1111111? You know, I don't even want to write it, so I just take a 1 and I lay them on the side and then I put them on the top. 0.1 repeat. So here's the cool trick you could do. What do you get when you multiply both sides by 10? I'll do this side. Oh, okay. So if I multiply both sides by 10, what happens when I multiply a number by 10? What does a decimal place do? It moves. It moves by 1, from your perspective, this way. It's 10 times bigger. Our number system is based on 10, so it just means everything kind of shifts. What was 1/10 becomes 1 when I multiply by 10. Is that cool? So that means When I multiply by 10, this is just going to move over 1. So now I'm going to have 1.1 repeated. So I had 0.111111. If I move this over once, now I have 1.1111. Excuse me. Yes, Jeff, make your point now. Okay, hold on. Does anyone see where I'm going? I forgot what I was doing. No, I'm joking. I'm not quite there yet. If I subtract both sides now, what's 10x? Oh my gosh, geez. What's 10x minus x? Go on. 9x. Good. I have 10x's. If I take 1x away, I have 9x's. What is beautiful about this? What was the worst part about this poor little dude? The infinite ones. Well, what do the infinite ones do? Cancel when I subtract them, yes? And 1 minus 0 is 1. Divide by 9. There. And if you put in your calculator 1 divided by 9, it will come back with 0.111111. So what is 2 ninths? Point 2. What is 3 ninths? 3. And what is 3 ninths reduced? 1/3. And you guys came in knowing that shit, yes? So what is 4 ninths? 4. Yeah, there you go. That's what I mean. So that is a very simple pattern. It's a repeating form. So if a fraction does not have, let me say it a different way. If a fraction has a factor on the bottom that is not a 2 or a 5, it's going to become a repeating decimal. That's kind of nifty. Do you all agree? Does anyone have a calculator out? Okay. What is 3 divided by 7? It's roughly 0.42 something. Keep going. What's it say?
0.428571428857.
There it is. See? Do you see how it started over again? It took it a while because 7 really sucks. 7. 42857 blah, and then 42857 blah blah blah. Yeah. So that is a long repeat. So 9 is nice. 9 is a nice number. It becomes a very nice repetition because it's kind of close to 10. That's part of the reason why it sucks. 7s kind of suck. But it does repeat. Do you guys see what I'm saying? So, real quick, just to show you one more example. What about you can do it, Jeff. 2424, repeating. So if I kind of turn this on its head, if I have a decimal that stops, I can automatically put that into fraction form, correct? You with me? Real quick, before we do this example, can you guys write this as a fraction? 0.1987256. What would that look like as a fraction? Whatever, Jeff. Just use something I told you earlier in reverse. How many places are there? 7. So how many zeros we have on the bottom of your fraction representation? 7. Of a particular set of skills. Okay. So this will be 1987,256 over 1, 1, 2, 3, 4, 5, 6, 7. So any decimal that already stops is a frickin' fraction. It wasn't written that way. You guys with me? Okay, how far you go? Billions of places, I'm just going to put billions of zeros. If I have a fraction, now do you all agree with me? This fraction does not stop. Okay. But it does have a pattern, a repeating pattern. If a decimal does not stop and has a pattern, so if it's non-terminating with a pattern, it will become a fraction. Numbers like pi. What's pi? Yeah, 3.14159. It never ends. That is truly irrational because you can't make it into a fraction, as far as we know. So. how do I make this into a fraction? Well, I say, I don't know what it is. Let me see if you guys can get the idea. What do I have to multiply it by? If I only multiply by 10, it's going to move over once, and then it's going to be 4, 2 that's repeating, and that's not going to cancel when I subtract. I don't know if you guys follow me. What was really nice about the thing we did before, I multiplied it by 10, and it was 0.1 forever, and they canceled with 0.1 forever. If I only move this over once, that's now 0.4242. That's not going to cancel with 0.2424. So what do I have to multiply by? 100. So if I multiply this side by 100, I multiply this side by 100, subtract, die, x is 24 over 99, that actually reduces to what? You guys see that? Yes, 8 33rds, yes? Trippydelic. Trippydelic. So if you put in your calculator right now, if you have one, can you put in there 17 divided by 99? Let's see what you get. What'd you get?
17 repeating.
Yes. 24 divided by 9, and it's 24 repeating. Isn't that kind of cool? Right? Screw each other. Just like 4 divided by 9 is 1 digit repeating. 24 divided by 99 is 2 digits repeating. If you did 117 divided by 999, you get 3 digits repeating. Okay, Jeff. Maybe? No? Yes? It would be very direct. I would say, convert this repeating decimal into a fraction. Yeah, this is a very direct procedure. It's one purpose in life is to give me a repeating decimal, I will give you the fraction. Yes. So my instructions would have to just say that. Yeah. I think they do talk about this process in the book, but I can't remember if I assigned a homework problem. Really, Jeff? You just teach this one? Be quiet. Blah, blah, blah. Okay. So, is everybody with me on that? So, what is the rule we could take? That if I'm given a fraction, let me ask you this, let me give you an example. If I'm given a fraction and the denominator only has factors of what? 2s and 5s, then it can become a terminating decimal. Yes? What do you guys think about this poor little dude? I only show it to him. So you show it to you. Put the board over here. What do you guys think about him? He seems alright. Jeff? Seems like a nice guy. He's just sitting there. What's the bottom half? Well, it's 5 times 5 times 3. But what saves his ass is the fact that the 3's cancel. Yeah. So you got to be careful. It's not just only the bottom you look at. If the bottom has an extra piece, take a second to make sure if it cancels or not. Yes. So it's if it's reduced and it only has 2s and 5s. Yes.
What is the, like, line and dot next to it? One.
So this is a equals, and this is a times. These died, so I get 1 over 5 times 5. I could be putting times since we're still doing that. Is that cool? Okay. And then of course you do like we did in the first place. You multiply by a couple 2's, you multiply by 4 to make it become a decimal, yes? Are you guys with me? Okay. How you guys doing? Have you ever heard of this before? No? Does it make sense?
Yes.
Okay. Alright. And you kind of knew it, you just didn't know how to put it into words. Yeah. This is one of those things, if you think about it, you're like, I kind of knew this, but I just didn't know to even put it together. All right. This involves a lot of mistakes from students. Let me give you an example. What do you think the mistake would be if I ask a student which one of those is bigger?
Looking up the lines.
Is that you raising your hand?
Yeah.
Or are you telling me an answer?
They might think it's 9.
Yeah, they might think it's 9. The student's gonna look at it and go, well, 9's bigger than 7, teach. Give me a hard one. And you're like, just go there. How do you take care of that? How do you help them see? Help them see. One thing you can do, what were they doing right before you started talking about this? Fractions. So going a little further back, we're going fractions, yes?
So what is 0.09 as a fraction?
9 over 100.
9 over 100. What is 0.7 as a fraction?
7 tenths.
They will know that in order to compare fractions directly, they have to have like denominator. So then, of course, 7 tenths are going to multiply by what to make it same denominator? 10. And that leads to a better thing than going to fractions, but that's what you do. That leads to making the number of places the same. But this explains why you can just throw on as many zeros as you want to, because math is like, that's going to cancel back to what it was. So you can throw in as many zeros as you want to there, Human. Have a good time. So now I look at that as a student and I go, oh, 70 is way bigger than 9. Instead of 9 is bigger than 7, right? That's kind of what you think. A little bit. Okay. Choo-choo! All right, let's see. Couple more things as I continue to slowly pass away. Let's see. Yes. What is this as a fraction? 1/4. What about this then? Let me do this for us. If I do that, I didn't change anything, right? It's still 1/4, correct? But what's the relationship here now? So I take half of 1/4 is 1/8. Good, yes. What about 0.375? I like what you're doing, but I did make it smaller. I made it bigger, right?
Yeah.
And to be honest, what I did was I added these together. So what's 1/4 plus 1/8? Well, it's 2/8 plus 1/8 is 3/8. Real quick, you guys follow. What's 0.250 plus 0.125? 375, correct? So I better add this side too. 1/4 plus 1/8 is 2/8 plus 1/8 is 3/8. So basically, if I know that 1/8 is this, 2/8 is 2 of these, 3/8 is 3 of these. Yes? Okay. And of course we all, 0.5. You'll never guess. That's crazy. Let me think. We know 0.33 repeating is 1/3. Yes? Let me think. That's enough for now. So what if I wanted to do this? You could do it, Jeff. Yeah. No, not that one. Let's do this. I don't have to do this the long way. I don't have to do 816 times 0.125 and blah blah, carry the blah. Why do I have to do all that shit? Because 0.125 is the same thing as the fractional equivalent of 0.125 is. What fraction is equivalent to 0.125? 1/8. So if I just replace this with what it is, why is that easy?
He's gonna put up one.
Yeah, 8 goes into 8, so that'll be 102. Totally. So the more fractional equivalents of decimals you know, the more you can do this. Now, to be really honest, that doesn't happen like often, but then that leads to estimation. And then I can use fractional equivalents to help with estimation. For example, well, before I get there, I'm sorry. Let me do a couple more examples that are just thinking strategies coming back again. What about if I had to do this weird shit here? (1.8) times 0.25 plus 0.25 times 2.2 and blah, blah, blah. Does anyone see we've done this before? What do they have in common? 0.25, right? So then I can undistribute it. Yes, we've done this before. Somebody distributed 0.25 to each of those poor little dudes, so let me undistribute him. Do you see how if I bring this in, I get this, and I bring this in, and I get this, yes? So I'm just doing that backwards. We've done that before. What is 1.8 plus 2.2? What's $1.80 plus 2.20? $4. And of course, 0.25 times 4 is 1. 4 quarters is the buck. Okay, I like it. Yes, yes, yes. Same old strategy we've used several times before. Just, it still works even if it's decimals. I almost forgot. I'm going to throw one in that's related to fractions just because I forgot to do it earlier. Let me see if I can come up with one. Yes, okay. Can I? Maybe. Oh, let me do this. Okay, here we go. 16 minus 8 thirds. Let's see if you guys are with me on this. Do you all agree 16 is 2 eighths? 2 times 8, yes? Yeah, whatever it is, 2 times 8. And 8 thirds is 1/3 times 8, yes? You with me? No? So this would be 8 times 2 minus 1/3. Not the best example I've ever come up with. Oh, that would have been a better example, damn it, Jeff. And then this would be 8 times 6 thirds minus 1/3 is 5 thirds, and blah, 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 you could do it, yes. Slightly better example would be like 8 minus 8 thirds. Yeah, that would be good, Jeff. This is a whole 8 minus 1/3 of an 8, which is 2/3 of an 8. It's kind of a different way of organizing the work in front of you. 8 minus 8 thirds is a whole 8 minus 1/3 of an 8, which is 2/3 of an 8, which is 16 thirds. It's a way that it's kind of using distributivity, but you don't have to actually rewrite it. A whole 8 minus 1/3 of an 8 is 2/3 of an 8, 16 thirds done. Do you ever have to do that in your whole life? No, you don't. It's okay. Sorry. I'll take it away. Nobody like that. Okay. Blah, 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 blah. Oh, here. Here's one that I've seen on various social media every now and again. people treat it as if, why don't teachers tell us this? They suck. And I'm like, they told you, you dumbass. I have to sit there and just yell at the screen. That, do you agree with me that that's not the best? Does everybody agree with me that multiplying by 0.5 is awesome? Because that's just cutting things in half, right? So let me show you kind of the long way to get to the shortcut. Do y'all agree with me this is 84 hundredths? Yes, maybe, no? So this becomes 84 times 50 hundredths, which is 84 times 0.5, which is easy. So as long as I'm dividing by 100 in the problem, it's the same problem. So I effectively can make, I'm kind of doing compensation. If I take 100 from this guy, I can give it to this guy. Make this guy 100 times smaller and this guy 100 times bigger. That's compensation. But then what's 84 times 0.5? You just cut them in half, right? I've seen this dumb thing. People, I'm sorry. It just gets to me. Especially order operations, you see them all the time. It's like, well, no. So let's just be 42.
Yay.
Okay. And then finally, the last one of these kind of mental math things. Oops. Did everybody see why that is really close to being easy? It's like, what's wrong with the person that made this? Oh, it's me. Why is it really close to being easy? Because I'm almost just subtracting. What am I almost subtracting? 5. And if I were just subtracting 5, that kicks so much ass. Well, then what can I use? Something we've used so many times. Not compensation. Equal additions, right? If I want to make 497 go up by 3 cents, I have to make 753 go up by 3 cents, yes. And then the distance between them is the same. So if I make this go up by 0.03 and this go up by 0.03, that would be 1756 minus 5, and that's easy as shit. What's 1756 minus 5? 12.56. Blah, blah, blah. Okay, so that's really good to remember. That's just generally useful. That equal additions. If you forget the name of it, I don't care. Just do it, and you're fine. All right. So let's see. The last set of ideas. We're doing good. We're having a good time. Oh yeah, this is kind of silly, but we'll be okay. This is kind of related, but it extends it a little bit more. What if I had Yes, I'm sorry.
Could you please go up just a little bit, sorry?
Sorry. I can go up all the way. Go up all the way. Do you see how that example, that new example, that 0.04 times 500, I could do something very similar? What does the 0.04 need to become a whole number? It needs to be multiplied by 1. I have to move the decimal how many times? 2. So I need something with 2 zeros on it. I need 100. Yes? So if I steal a factor of 100 from basically here's what you can boil it down to. So here's the full-blown thing, and I'll show you the shortcut. Oh, you can't see what I'm doing. Get here. Go to there. Go. Yeah. Okay. Whew, that's a long ass way to go for that. So I write this as 0.04 times 5 times 100. I take the 100 and I give it to the 0.04. That makes it a full 4 times 5 is 20.
Yay.
The shortcut is if you take 1, 2 back here, you can go 1, 2 forward there. 4 times 5 is 20. Thank you. That's compensation. The 500 is given 100 times to the 0.04, making it a whole number, and the answer is easy to do. Yes? That is the idea we just did a minute ago, but more generally. Just take what you need from one guy, give it to the other guy, you're gold. So here, you guys do this one. That'll be fun, yeah. I don't even know. I'm not sure what kind of problem it's made. Oh, okay, I made it easy for him. Wasn't paying any attention. So where you start is the decimal number. What does he need? How many times does he need this decimal move to become a whole number? 6 times. So then how many zeros do you take off of the other two? 6, because each 0 represents a factor of 10. If you steal a factor of 10, or let the guy give you compensation, a factor of 10, your decimal moves once. If I need to move 6 places, I take 6 factors of 10, which translates to 6 zeros. So if I take 6 factors of 10 from this guy, I can then move my decimal 6 times, and I get 2 times 14 is 28. Crazy. Yes? Compensation.
That's dividing by whatever those.
Do you?
That's dividing by a million, right?
Oh, yeah.
Okay.
If you multiply the 0.2 by a million and you divide the 14 million by a million, that's direct compensation. Yes. I don't care too much about that. Here, this one, okay. All right, let's start nice. Can you guys round that decimal to the 10th place? Round it to the 10th place. One really good thing to do is to find the 10th place and underline it. Yeah, you're 4.1, right? Because the next number after the 10th place is a 2, 4.1, so it's the 10ths. Can you round this to the, what you got, Jeff? 100th place. Yeah, right? If you find a 100th place, you underline it, you look next to it, that's bigger than 4. All right, it's 5 and up, so it's gonna be 4.13. So here's the trick. What about 4.4449? Can you round this to the 100th place? I don't know why this is tricky, but it is. So I want to talk about it directly. It isn't tricky. It isn't. I get people that argue for certain weird things to happen. Don't overthink it. I don't overthink it. I shouldn't have said a damn thing. Damn it. I made people think it's more than I think. No, it isn't. That's the problem. What's in the 100th place? Well, you can't go wrong if you say 4, but. So here's the 100th place, yes? What's next to it? So then what do you get when you round it to the 100th place? Now, can anyone see how somebody could actually do something different? Somebody who understands how to round by itself, but there's, I call it dominoes, the thing that happens. Not the pizza, but the little parts, the little things. If I said rounded to the 1000th place, then what happens?
4.445.
That would become a 5. So somebody says, wait a minute. Wait. If that would become a 5. And then that would become a 5. And then that would become, and that's the domino effect, yes? If I say round to this place, the only thing I give a shit about is what's the immediate next number. That's all. I don't give a crap what the next numbers after that are. You with me? I see this so many times though, I have to hit it directly. Other numbers can't come in and go, let me come by the, get out of here, I don't care about you, I only care about the number right next to the one I'm looking at, right? But I wanna be part of the, get out of here. Be quiet now, get out of here, okay. Last idea. Good timing, here we go, estimation. Estimation. I want to first start off with an idea I keep bringing back up. That looks good. Good Lord, no it doesn't, Jeff. What is that supposed to be? 47.19, there it is. Gosh, if I could just write, it would be amazing. Your life would be so much easier if my third grade teacher had made me stay after school. There was like a knitting thing after school for kids that needed help with their fine motor skills. If she would have forced me to do that, I would have made it right. But this is what you guys get. So I'm sorry. I want to estimate this. There's an idea I keep bringing up. If I have a multiplication problem and I round a piece of it down, I have to round the other piece up. So that overall the answer comes out close to right. Yes? You with me? What's 10 times 2? 10 times 2 is 20. 5 times what is 20? 4. So if I make 10 go to 5, 2's got to become 4 so that the answer is the same. So if I'm going to estimate, obviously I want to round this which way? Up or down? No. I want to make it whole. I want to do this in my head. I want as many zeros as possible. I'm going to make this 400, yes? So this went down, so what am I going to do with this one? Go up and make it 5. What's 400 times 5? 2000. Yes, 2000. You guys with me? So this idea I keep trying to push on you, if I have a multiplication problem, I got to go up and down. If I have a division problem, they have to go the same way. 20 divided by 2 is 10, 30 divided by 3 is 10, 40 divided by 4 is 10, they have to go the same direction to stay the same. Do you have an example like that, Jeff? Yes, I do. Look at it go. So like, for example, if I had 29.35 divided by, I'm going to change it on the fly, why not? 2.87. Ugh. Sorry. I am loopy. So then, I desperately want 29.35 to become what? 30. So I made it go up. I want to make the other guy go up also, yes? So this becomes 30, this becomes 3, and that's 10. That's my estimate. To check yourself, you can obviously do the original problem and see that you came close. Anything else that's really sort of, here's an idea using fraction equivalence. What fraction equivalent is this close to being? What decimal that becomes a fraction, a nice fraction, is this close to? .25 is what is a fraction? Is that close to 0.25? Yes. If I make this become 0.25, did I take it up or down? I went down, so I better go up on this. And what kind of number do I want this to become? 0.25 is 1/4, so I want to round this up to be a number that 4 goes into. So what is this kind of screaming at you? 88. You guys see what I'm saying? We're estimating. As long as I try to keep the balance, I can make it whatever the shit I want to. I could have made it 89. Why would I do that shit to myself? I'm going to make it 88, because then 88 times 1/4 is freaking... 4 goes into 88. Yes. Who's got the calculator, real quick? Who's got the calculator? What is this? Do 85.372 times 0.278. See how close I got. I got a feeling that, let me see. Wait. I think it's too, I don't know. I think it's too small. I don't know. What is it?
23.73.
Yeah. 23.7 blah, blah, blah.
Yeah.
Was that decent? Yeah, it's good enough for government work. Okay. Yeah, my next page is blank. We have reached the end of my lecture notes. We are done. So you guys, hopefully, whatever you plan to do tomorrow, hope it goes well. I will see you next week. Have a good weekend.